Hello everyone. I hope you're doing good today. Before we go to our next lesson or topic, let's review first the polar and nonpolar molecules based on their difference in electronegativity. So again, there are two types that you need to keep in mind if we're basing the difference in electronegativity. You need to also keep in mind the shape of the molecule, if it is symmetrical or asymmetrical in shape. Like for example, let's start with a symmetrical shape of the molecule. Below zero point 0.4, the asymmetrical shape molecule is nonpolar. Okay, that's the one that we did before. And if it is in between zero point 0.4 and 1.8, that's polar covalent. Okay, why it is polar covalent? Because if we say a symmetrical shape, it means the electronegativity difference is between zero point 0.4 and 1.8, and there's nothing that can cancel the electronegativity of the molecule. Even though there are electronegativity on each end of the around the central atom, even though there are different electronegativity, if nothing can completely make it zero, then that molecule is a polar covalent compound. So that's if the molecule is asymmetrical in shape. Now, what happens if it is over 1.8? Some books, they're using 1.7 as the boundary. That's okay. So let's just say 1.8 and or 1.7. If it is over 1.7 or 1.8, that is no longer covalent compound. That is now ionic compound. Okay? And why? Because the difference is now too big that one of that element of those elements give up their electrons or electron, and that is a metal. That's why we call that ionic compound. One is giving their electron or electrons, and one is receiving the electron or electrons. Now, that is true for all asymmetrical shape. Nonpolar for less than 0.4 difference in electronegativity. Polar if it is between 0.4 and 1.8. Ionic compound if it is now beyond 1.7 or 1.8. Now, what happens if the shape of the molecule is symmetrical? Remember, if it is symmetrical, it means the surrounding atoms of the central atom, so it means the other atoms outside the central atom, are the same. So we can consider that as symmetrical if the surrounding atoms are the same and they are distributed equally outside. That is symmetrical, and they can cancel out all their electronegativity. Okay, so that is symmetrical in shape. So symmetrical in shape could be linear, it could be cross, or it could be triangular. So even if it is triangular, it could be that is also symmetrical as long as the surrounding atoms are the same. Like if it is hydrogen, hydrogen should be surrounding the central atoms. If it is fluorine, fluorine should be surrounding that central atom. So what happens to the polar, nonpolar for the measurement of their difference in electronegativity? If it is less than 0.4, of course, it is always nonpolar covalent compound. But here, if we're talking about symmetrical shape between 0.4 and 1.8, it will still be nonpolar covalent compound. And what is the reason why we see, or why we can say that it is a non-polar covalent compound? It's because it is symmetrical, although they have a difference of between 0.4 to 1.8. Those number or value of difference in the electron negativity will be canceled out by the other difference of electronegativity in its surrounding. So it will give us non-polar answer. Okay? So if it is symmetrical, even though it's between 0.4 and 1.8, it will be considered non-polar covalent. And beyond 1.8 or beyond 1.7, it is still ionic compound. It won't change. Okay? I hope you keep that in mind. So the only thing change is the between 0.4 and 1.8 for both a symmetrical and symmetrical shape. Now, since we're talking about shapes, let's talk about shapes. And the theory VSEPR, or valence shell electron pair repulsion theory, is the one responsible in predicting the shape of molecules. How? How do we determine the shape of molecules using this? We are predicting the shape of molecules based on how the electrons are pushing away each electrons. So just think of them as couples that want their space, and they don't want other couples to be moving closer to their space. So as much as possible, they're trying to find the farthest distance that they can be, because they have their own space. They want to stay in their own space. Okay, so just think of it as like a space bubble that they want to stay, and they don't want others to stay in that space bubble. And that entire space bubble of the couple of electrons will be creating the shape of the molecule. So that's why VSEPR, which is talking about the repulsion of the electron groups, is the reason why we can predict the shape of the molecule. Like for example, the shape of carbon dioxide is showing us linear shape, while the shape of water, H2O, is bent shape. And we're gonna discuss that. We're gonna look at why water is bent and why carbon dioxide is straight. Let's talk about electron pairs. If we say electron pairs, it talks about couple or group of electrons. In bonds, it could be double bond, single bond, or triple bond. So in the single bond, there are 2 electrons involved as one group. In the double bonds, it has 4 electrons in one group. In a triple bond, it has 6 electrons in one group. Okay, so just think of electron pairs or electron group as just group of electrons that want to stay on a particular space. Okay? For example, if you hear the word electron pairs, sometimes they will say electron domains, sometimes they will say electron groups. For example, we have NH3. Remember, the first molecule here is NH3. We write first the N, nitrogen, because it's the central atom. Although it is not organic molecule. Remember, all organic molecule means it has hydrocarbons. If it has hydrocarbons, it means it is an organic molecule. So NH3 doesn't have hydrocarbons, so it's not an organic molecule. Remember the IUPAC rule that you need to start with carbon first, and then second is the hydrogen, and then the rest will be alphabetical order. So that's the convention for organic molecules. But for inorganic molecules, as long as you can actually do it in any way, It could be central atom first and alphabetical afterwards, or lower electronegativity first and going to the higher electronegativity after. Okay, so that is for inorganic molecules. But for organic molecules, you should always start with C, second is H, and the rest will be alphabetical order. But here, since these are inorganic molecules, so we can actually just decide to start with the lower electronegativity to name the formula. But here, since we already know the central, it's nitrogen, so we can say it's N and then H3, because there are 3 hydrogens, NH3. How many electron groups do we have here in NH3? We have 4. And why? First group is the lone pair. Remember, if it is already paired, we call that lone pair. And that is one group. Second, and third, and fourth are the bonds. Okay, so the single bonds are surrounding the nitrogen. Those are also groups. First, second group, third group, and fourth group. So all in all, you have 4 electron groups in our molecule. Okay, so that's what it means by groups. And here in our next molecule, since the center atom is O, so we're going to start with O, and we can call this as OCl2. OCl2, because there are 2 Cl. That is not Ci, that's Cl, chlorine. Okay, now how many electron groups do we have here in OCl2? We have 1, 2, so we have 2 lone pairs, so that is already 2 electron groups, and 2 bonds. So we have all in all 4 electron groups. So those are the things that you need to focus on. Now, you might be asking, how about those lone pairs on Cl? No, we are only concerned the electron groups or the electron pairs surrounding the central atom. Only the electron groups surrounding the central atom. So the lone pairs of Cl will not be included. Okay, here in our compound, the second compound or second molecule, we only have 4 electron groups. And those are the things you need. You need to know first so that you can predict the shape of the molecule. Okay, and how do we do that? Let's start. First, let's arrange them into which one is occupying larger space or the largest space. The lone pair is the one occupying the largest space. So lone pair is really like strong. It can push away all other electrons, especially the bonds. So lone pair is, just think of it as they are the power couple. They want to acquire a bigger space compared to other molecules. Other bonds or electron groups. If we see lone pair around the central atom, we can now say, oh, this part of the central atom will be occupied largely by the lone pair. And the rest of the electron groups will be pushed away by that lone pair. Okay, just think of it that way. So, for example, let's try the tetrahedral shape. And what is the tetrahedral shape? Tetrahedral shape is like a pyramid with only 3 faces that you can see. But actually, the reason why we call that as tetrahedral, it's because it has 4 faces. Okay, and why is it 4? It's because we count the bottom part as face as well. So that's why it's called tetrahedral shape. But just think of it as a pyramid with just 4 sides. Okay, 3 sides, because the fourth one is the bottom one. Okay, and it looks like this, like the Jockstones game. If you have played that, but it's not really the same as the Jackstones, because the Jackstones it has like eight ends, right? Yeah, one, two, three, four, five, six. No, six. But here we only have four, and they are equally far away from each other. Okay, and why is it equally far away from each other? So let's have an example. CH4, methane. Okay, this is a organic molecule or compound, which is, we have C and combined with H. So that's organic molecule. It means C is our central atom because it's written first. And the four hydrogen are the atoms surrounding the central atom. That's it. And they will be sharing their electrons because that's covalent compound. Covalent compound always share electrons. And we will be using lines representing the shared electrons. And we can now see that we have four electron groups, which are the single bonds, right? So we have four electron groups. Now, if you observe the diagram itself, you might be saying, they are already equally far away from each other. Are they? Yes, they are far away from each other on a flat surface. But remember, molecules are occupying a 3D or three-dimension space, not a plain surface. Okay? So, they are equally far away from each other on a plane surface or a flat surface, but in an actual 3 dimension, they are not they are not equally far from each other. And to do that, they need to, as much as possible, use the front of this screen and the back of this screen to be far away from all the other single bonds. So just look at the single bonds. Those single bonds, they want to be as far away from each other. They will be forming like this. And that is the farthest that they can do away from each other. Each bond, if you pair each bond, they will be approximately 109.5 degrees away from each other. Each one of them, if you pair them two bonds at a time, they are equally approximately 109.5 degrees away from each other. Okay, and that's why we call this as tetrahedral shape, because if you form this, it forms a tetrahedral. Now, next is the trigonal pyramidal shape. Okay, just imagine trigonal pyramidal as tetrahedral, which is smaller in height. Okay, and why is it smaller in height, and why is it still tetrahedral? Example, ammonia, which is NH3. So our central atom is N, nitrogen, and the surrounding atoms are 3 hydrogen. Now look at this. How many electron groups do we have? We have 4. 1 lone pair and 3 single bonds. Right? 4. Now again, each one of them are trying to move far away from each other using the 3-dimension space. The lone pair is stronger in repulsion. So it's trying to occupy a bigger space here on top. While the rest, they're trying to do their best to be far away from that lone pair and to be far away from each other single bond as well. So they form like this. And that lone pair that creates that like bubble thingy, it is actually invisible. We cannot see it because it's a lone pair. There's no atom there. So if there's no atom present, it means it is just creating that space without an atom, pushing away the single bonds with atom, And the ones with atom are the ones creating the shape of the entire molecule. So if there is no atom, it means this part here on top, which is where our lone pair is located, it means it's invisible. So it will turn like this. So that top there is actually invisible. So the only shape that we can see is the bottom part where there are atoms present. Okay, and how far away those bonds to each other? This time, since the lone pair is present on top, it looks like a tetrahedral. But again, since it's invisible on top, we now call this as trigonal pyramidal shape. Okay, so another example. Since the lone pair is pushing more the single bonds, then the single bonds are now closer to each other. Okay, a while ago it's 109.5 degrees, but right now it's 107.5 degrees, since the lone pairs are stronger in repulsion, pushing down more the single bonds. That's why their angle is also decreased. They're now closer to each other. So another example is the bent shape, which is we made water as our example, H2O. We have here central atom as O, and the surrounding atoms are hydrogen. And how many electron groups do we have here? We have 4. The 2 lone pairs and 2 single bonds. So these are the electron groups that we have. And again, look at this drawing on the right side, or the illustration on the right side. The 2 lone pairs are trying to occupy a bigger space, forcing the 2 single bonds trying to move away from each other, but closer now to each other, because the lone pairs are trying to occupy a bigger space, like most of the entire space of the molecule. Again, these lone pairs are just occupying the space, but since there's no atom present on those lone pairs, they are invisible. So if we take them away, the remaining shape will be just like this. If we look at that, it's a bent shape. So that's why we can see molecules of the water as bent shape. Okay, now let's try to use this table and understand how to do or to predict the shape of a molecule. Okay, for example, let's start with the first column. The first column says the first cell, or the first square. It says 2 electron groups. So let's start with the 2 electron groups. If there are 2 electron groups, the possible shape is linear. And why linear? Because in the 2 electron groups, there's no lone pairs involved. And the VSEPR notation is like this, AX2. And what does it mean by AX2? AX2 means the A is the central atom, any central atom. It's just representing the central atom. The X means the number of bonds. So how many bonds are present in your molecule? So in our example here, carbon dioxide, we have 2 double bonds. So there are 2 bonds present in our molecule. And if there are 2 bonds present with a central atom, then those 2 bonds are trying to move away from each other as much as possible, and they can create 180 degrees away from each other. So carbon dioxide is a linear shape. Okay? And by the way, I forgot to mention, VSEPR theory to predict shape can only be used if you have a central atom. Okay, remember in our fourth column here, it talks about the central atom. So you need to have a molecule with central atom for the VSEPR to be used. If you don't have a central atom, then you cannot use this to predict the shape. You can use a different method. Now, let's go to the three electron groups part. So there are two possible shapes that you can create in a three electron groups. One has two bonds and one lone pair, and the other one has all three bonds. Okay, for three electron groups, it could be three bonds all in all, or two bonds and one lone pair. So let's start with three bonds. So meaning the lone pairs is 0. So the notation, the VSEPR notation is AX3. And what does it mean by that? Again, central atom is the A. X means the number of bonds. So we have 3 bonds. And what is the shape? It's trigonal planar, which is flat. It is flat shape. And why is it flat? It's because that is already the farthest distance that 3 bonds can do. Just imagine it. If you have 3 bonds, the only way that you can separate them is being just in a flat surface. So that's why we call it trigonal planar. It's a plane triangle. And the example of this is the BF3. So they can create a 120 degrees away from each other. That's exactly 360 divided by 3, right? The BF3 could create 3 bonds surrounding the B as our central atom. Now, let's have the 3 electron groups, the second possible answer of the 3 electron groups, which is 2 bonds and 1 lone pair. So the VSEPR notation is AX2E. And what does it mean by E? The letter E describes the lone pair. So if it is just E without a number, it means 1 lone pair. If it is E with 2, it means there are 2 lone pairs. Okay, you can see that later for other examples. Why is it also bent for this? Okay, because look at the lone pair. The lone pair occupies the other end of that triangle. And remember, the other end does not have an atom. So the lone pair, it doesn't have an atom on that end. It's invisible. So if you take that away, it will be a bent shape. So example is NOF. Actually, you can write it as NFO or NOF. We put the N first because it's the central atom. So what happens here? We have 2 bonds and 1 lone pair on the top of the nitrogen. So that is already 3 electron groups. That's why it belongs to the 3 electron groups. And since the lone pair is taking space but invisible, the entire shape will be a bent shape. Okay, next one. Now let's have the 4 electron groups. And there are 3 possible shapes in 4 electron groups. The first one is 4 bonds, which has 0 lone pair. So that's the first line. And we call that as tetrahedral. tetrahedral, the one that we had in our example. So tetrahedral, AX4. X means number of bonds. We have 4 of them, so that's why it has 4. So example is CF4. The only shape that they can do is the tetrahedral shape, and they could create an approximately 109.5 degrees away from each other, from each bond. So that's why we call this as tetrahedral shape of molecule. The next possible for 4 electron groups is 3 bonds and 1 lone pair. So the VSEPR notation is AX3E, just E, 1. So it means 3 bonds and 1 lone pair. Example, NH3. NH3, 3 bonds surrounding our nitrogen and 1 lone pair on top. So that top lone pair is occupying a lot of space, forcing the bonds, the single bonds away, and the single bonds are also forcing away from each other. That's why it forms the trigonal pyramidal, since the lone pair occupying the space on top, but it's invisible. So it formed like a tetrahedral but smaller, and we call that as trigonal pyramidal shape. Now the third possibility is the 2 bonds and 2 lone pairs. The VSEPR notation is AX2, 2 bonds, E2, 2 lone pairs. Example is water, H2O. So we have bent shape because it actually shaped as tetrahedral. The other ends are the lone pairs, but the lone pairs are invisible. So all we can see is just the ones with the atoms, which is shaped as bent shape. And they have an approximately 104.5 degrees away from each other, the single bonds. Okay. Next, we're done with the ionic compound and covalent compound. That was the last part of the covalent compound, knowing how to use the VSEPR theory to predict the shape of the molecule. Now let's talk about the naming of acids and base. Now acids and base behave as an ionic compound. They are like ionic compound, but they also behave as covalent compound because they're sharing electrons. Now, acids, they produce hydronium ions when placed in water. So if you have HCl, which is a pure HCl substance mixed with water, it becomes an acid because it produces this H3O plus, which we call that as hydronium. And acids usually starts with H, but not all of them, okay? Keep that in mind. Not all of them, there are exceptions, but right now let's just focus on those acids that start with H. So one of them is HCl, which is creating a hydronium once dissolved in water. Next, bases. What are the indicators to know base? Okay, most of the base, just like acids, it starts with H for acid. For base, it ends with OH. Okay, most of the bases, not all. Because some base, like ammonia, it is NH3, which is also a base, but it doesn't have OH at the end. But that NH3 could also release hydroxide ions, just like this. NOH, dissolved in water, and it created the hydroxide ions, or OH negative. Now, we're going to focus on the acids that starts with H, the bases that ends with OH. Okay? And we're going to name them. And how do we name them? First, the nomenclature, or the naming of acids, rules that we need to follow. The acids, first, if we focus on the binary acids, it means H paired with nonmetals. So any nonmetals paired to H will be the binary acids. Example, HBr. So how do we name this? The rule for this is starts with the word or prefix hydro. And after the prefix hydro, put the word of the non-metal that you use. And change the IDE form into IC. So for example, the anion form of bromine is bromide. So instead of bromide, it becomes hydrobromic acid. Okay? Instead of hydrobromide, it becomes hydrobromic acid. Next, HI becomes hydroiodic acid. Easy, right? Next, HF is hydrofluoric acid. HAT becomes hydroastatic acid because it's acetate. Just change the IDE into IC, add hydro at the beginning, and it is already acid. For H2SE2, it's selenide, so it's hydroselenic acid. Now, why is it H2SE2? Why the others are with one H? But here we have two H and two. Oh wait, the two in SE, that's supposed to be not there. That's typo. But the H has two. And why does it have two? It's because if we treat them as ionic compound, remember H is H1 plus, Se is Se2 minus. If we crisscross them, it becomes H2Se. And that's why it gives us the H2Se without the 2 at the end. So that's how you name binary acids. Next one, oxyacids. Now for oxyacids, we're gonna use the polyatomic anions, not the cation. Although there is a cation involved, the ammonium, we're not gonna use that. We're gonna use the anions, the ones with negative, okay? Negative oxidation number. So how do we use this? How do we name these acids with polyatomic ions? For example, HNO3. And where are these examples? I encircled them. Let's start with HNO3. Now, on how do we write them is just like the ionic compound, we crisscross their oxidation number to form the chemical formula. So let's start with HNO3. NO3 is nitrate with ATE at the end. So if the suffix, we call that suffix, that the end connection letters, if it ends with ATE, you change that to IC. and then add acid at the end. So instead of nitrate acid, it becomes nitric acid. Easy, right? Now, here, H2SO3, which is sulfite. And by the way, why is our H here becomes 2? It's because SO3 here, the sulfite, has 2 negative oxidation number, charge number. So if you crisscross them, the 2 will go to H. Okay, that's why it's H2SO3. Now, how do we name this? Now, most of the misconceptions for sulfur, if it involves with sulfur and phosphorus, you need to keep this in mind. If you need to change sulfur word into acids and phosphorus word into acids, you need to add some of the other letters of that element. Like for example, sulfur. Instead of sulfite, make it following the ITE rule that change into OUS. Instead of sulfus, you need to add the UR of the sulfur and then add the OUS. So it becomes sulfurous acid. Okay, that is only true for sulfur and phosphorus if there are sulfur and phosphorus involved in the acids. Okay. Another example, HClO3. ClO3 is chlorate. So ATE. Change that to IC. It becomes chloric acid. And that's it. That's how easy it is. How about this one? PO4. PO4 is phosphate. And since we are involving phosphorus, instead of ATE must be changed into IC. Instead of phospic acid, it will be phosphoric acid. So you're going to add the OR of the phosphorus. Okay? So phosphoric acid. So this is only true for sulfur and also phosphorus. Now, okay, that one is, yeah, the PowerPoint is messed up. That one is the answer for number 4. Number 5, BRO has 1 negative. So that's supposed to be just a HBRO 2. Okay, because it's 1 negative. During crisscross, that's supposed to be just H and then BRO2. So BRO2 is bromide. You just need to change the ITE into OUS. So the answer is bromous acid. So that's how you name acids, whether it's a binary acid or an oxyacids. Now for bases. Nomenclature or rules in naming bases. Let's start with the one with the alkali metals and alkaline metals, the first and the second group in the periodic table. Remember, they will create 1 positive and 2 positive if we change them into ions. So again, bases also follow the same behavior as ionic compound. You crisscross them to form their chemical formula. But we're using OH as their anion. OH 1 negative. So first example, LiOH. So how do we name this? Remember, in naming metals, it should be only just metal. Lithium hydroxide. Since OH is hydroxide, just lithium hydroxide. Na is sodium, and OH is hydroxide, so sodium hydroxide. K is potassium, OH is hydroxide, so that's potassium hydroxide. Ca, calcium, OH is hydroxide, so it's calcium hydroxide. But in the formula, why does it have 2 parentheses to our OH? It's because Ca is 2 plus and OH is 1 negative. So if we crisscross that, the 2 will be now as a subscript of our OH. So we need to put that in parentheses and put 2 outside. Now B, the same as barium as well. Barium is 2 plus. That's why the OH also in parentheses and 2. So since it's barium and hydroxide, it's barium hydroxide. And that's it. And another way to name bases is using the transition metals. And this is the same thing we did in transition metals. However, like the ways that we name transition metals using parentheses with Roman numeral. Like for example, FeOH. OH is already hydroxide. Fe is iron. But Fe is a transition metal. So what is the parenthesis of that entire name of that base? You need to figure out the oxidation number or charge number of that iron. So the charge number of that iron is 2 plus. And where did I get the 2 plus? The one found outside the parentheses of OH. Because if you crisscross them back, that Fe or iron will receive 2 plus, right? So that's why it's iron 2 hydroxide. The same thing for number 2, iron 3 hydroxide. For 3, copper. Copper 2 hydroxide. Cr, chromium. Chromium 3 hydroxide. And Pb is lead. Lead 4 hydroxide. And that's it. That's how you name acids and base.